Welcome to today's paper reading. Today's paper is titled, Is Cosine-Similarity of Embeddings Really About Similarity? This paper was published on the AR14 preprint by Harald, Steck and colleagues from Netflix Incorporated and Cornell University. Cosine similarity is a measure that quantifies the similarity between two vectors by calculating the cosine of the angle between them. This is equivalent to the dot product of the vectors after normalization. It is widely used to assess semantic similarity in high-dimensional spaces by applying it to low-dimensional feature embeddings. However, in practice, it sometimes performs better and sometimes worse than the unnormalized dot product. To understand these empirical findings, the authors examine embeddings derived from regularized linear models, which allow for analytical insights due to their closed-form solutions. They find that cosine similarity can produce arbitrary and meaningless similarities in some cases. For certain linear models, these similarities are not unique, while in others, they are controlled by the regularization. The implications extend beyond linear models, as different regularizations are combined in deep learning models, leading to implicit and unintended effects when cosine similarities are taken of the resulting embeddings. This makes the results opaque and possibly arbitrary. Based on these insights, the authors caution against the blind use of cosine similarity and propose alternative approaches. In this paper, the focus is on how discrete entities are embedded into dense vectors across different domains. For example, words in large language models are embedded based on their context, and items in recommender systems are embedded based on user consumption patterns. The advantages of these embeddings include their use as inputs for other models and their ability to provide a data-driven measure of semantic similarity. While cosine similarity is widely used to measure semantic similarity, it has been found to sometimes underperform compared to the dot product of embeddings. This paper aims to clarify these inconsistencies by examining the properties of learned embeddings and proposing analytical solutions, particularly for linear matrix factorization models. In this section, we delve into the matrix factorization models, focusing on linear models which allow for closed-form solutions. This facilitates a theoretical understanding of the limitations of the cosine similarity metric applied to learned embeddings. We consider a matrix X as an element of Rn times P containing n data points and P features, aiming to estimate a low-rank matrix A. B down TAC is an element of Rp times P, where A, B is an element of Rp times K with K less than or equal to P. The rows of B are referred to as item embeddings, while the rows of XA are interpreted as user embeddings. The model is defined in terms of the dot product between user and item embeddings. During training, two regularization schemes are commonly used, differing in their L2 norm regularization. The first objective applies L2 norm to their product, equivalent to learning with denoising, leading to superior prediction accuracy. The second objective regularizes each matrix separately, similar to weight decay in deep learning. Notably, the first objective is invariant to rescalings of the columns of A and B, introducing an arbitrary diagonal matrix D that affects the normalization of the learned embeddings and consequently, the cosine similarity. In this section, we discuss remedies and alternatives to cosine similarity. One approach is to train the model with respect to cosine similarity, which can be facilitated by layer normalization. Another strategy is to avoid the embedding space altogether and project data back into the original space. Regarding normalization, it is crucial to note that it is typically applied after the embeddings have been learned, which can reduce semantic similarities. In deep learning, common techniques include negative sampling and inverse propensity scaling to account for item popularity. For example, in Word2Vec, a matrix factorization model was trained using negative sampling with probabilities proportional to item frequency raised to the power of beta equals 3/4. Figure 1 illustrates the significant variability in item-item cosine similarities, COSIM, BB, on the same dataset due to different modeling choices. On the left, the ground truth clusters are shown, with items sorted by cluster assignment and popularity. The center 3 plots demonstrate the effects of 3 specific rescaling choices after training with EQ1, which allows for arbitrary rescaling of singular vectors in VK. The right plot shows the results from training with EQ2, which yields a unique solution for the cosine similarities. This figure highlights how different modeling approaches can lead to vastly different cosine similarity outcomes, even when applied to the same data. In this experimental setup, the authors simulated interactions between 20,000 users and 1,000 items, which were grouped into 5 clusters. The power law exponent for each cluster was sampled, and a baseline popularity was assigned to each item. User-item interaction probabilities were then computed. The matrices A and B were learned under a low-rank constraint of 50, contrasting with the full-rank model. The study focused on analyzing cosine similarities obtained from training with respect to 2 equations, highlighting the differences and resulting similarities due to rescaling and unique solutions. In this study, the authors examined the use of cosine similarity in linear matrix factorization models. They highlight that the effectiveness of cosine similarity is heavily influenced by the method and regularization technique used. In some cases, it can even be rendered meaningless. The authors support their analytical findings with experimental data, using simulated data where ground truth item-item similarity is known. Based on these insights, they advise caution against the blind use of cosine similarity and propose several approaches to mitigate these issues. While the study is limited to linear models, the authors anticipate similar, if not larger, problems with cosine similarity in deep models due to the combination of various regularization methods and the different layers implicit scaling of latent dimensions. Thank you for watching.